Ngalakin kadijan nyunga boja.
All right, it's 3 o'clock. Good evening, everybody. Today, I'm delivering this lecture via Zoom. Of course, the lecture is also available, recorded in Echo 360 for later use. Today, we're going to look at Chapter 6. Chapter 6 is on asymmetrical faults in a power system, and also this chapter, there is the last final section on this chapter is on power system protection. So the first part is on asymmetrical faults in this chapter. In chapter 5, we've looked at symmetrical faults. In other words, three-phase to ground faults. They are symmetrical. And today we're going to look at the other types of faults which are asymmetrical. So the asymmetrical faults are a single line to ground fault. Like if a line is connected to ground, obviously that's a symmetrical fault, and that's called a single line to ground fault. We can also have line-to-line faults. In other words, two lines connecting to each other. That's a symmetrical fault as well. We can also have two lines connecting to ground, and that's another asymmetrical fault. System in this situation, we assume it's only unbalanced at the point of fault. Everywhere else is balanced. In other words, the generators are balanced. The transmission line impedances are balanced. But at the point of fault, with these three types of fault, single line to ground, line to line faults, and double line to ground faults, at the point of fault, the system is unbalanced. Now, the easiest method to analyze unbalanced system operation due to faults is through the use of symmetrical components. So, what is symmetrical components? The key idea of symmetrical component analysis is to decompose the system into three sequence networks. So we have one network, which is phase A, for instance. We decompose that into 3 sequence networks. The network, sorry, yeah. I was expecting more people to be there joining online, but maybe everyone's studying for the test tomorrow, perhaps that could be it. So the key idea of symmetrical component analysis is to decompose the system into 3 sequence networks. The networks are then coupled only at the point of the unbalance or the fault, because that's where the unbalance situation occurs. So at that point, the 3 separate networks will join together. Otherwise, they are decoupled. The 3 sequence networks are known as the positive sequence network, the negative sequence network, and also the 0 sequence network. So these 3 separate networks that we will introduce. The idea was first presented in 1918 by Charles Fortescue, and I've given reference for that work if you're interested in looking further into it. So positive sequence set, what is a positive sequence set? So if you have a voltage A1, so imagine a voltage A1, B1, and C1. So VA1, VB1, and VC1, they are 3 separate voltages. They have identical magnitudes, and since they are a positive sequence set, VB1 is actually 120 degrees behind VA1, and VC1 is 120 degrees behind VB1. So that's a positive sequence set. So we're talking about a positive sequence voltage set. All the magnitudes are same, and they just differ by the phase angle. And we've seen that sequence when we talked about balanced 3-phase systems. The sequence ABC is B is 120 degrees behind A, and C is 120 degrees behind B. So if you're talking about a voltage, they will all have the same voltage at point A, VA, VB, VC. So the 3 separate phases, the magnitudes are the same, but they differ by the phase angle. Now a negative sequence set is negative sequence set. It's the sequence is actually reversed. So VB, instead of lagging 120 degrees, it will be 120 degrees in front of VA. And VC2, instead of being behind VB by 120 degrees, it will be in front of VB by 120 degrees. So a negative sequence set is drawn here. If ABC is a negative sequence set, then this diagram here shows the voltages A, B, and C. And we call it VA2, VB2, and VC2. And the positive sequence set, the voltages we denote VA1, VB1, and VC1. Now the 0 sequence set, all the voltages are identical in magnitude, and they are parallel. So they have the same magnitude and the same direction, the positive sequence set. So the idea about introducing a positive sequence set, a negative sequence set, and a 0 sequence set is now the voltage VA is defined in terms of those 3 components: the 0 sequence magnitude, the positive sequence magnitude, and the negative sequence magnitude. So VA is equal to VA0, 0 sequence for voltage A, VA positive, positive sequence for voltage A, VA minus, negative sequence for voltage A. So we can then say the same thing for VB. VB must be its 0 sequence component plus its positive sequence component plus its negative sequence components. So imagine a particular voltage, either VA or VB or VC, we just break it up into 3 parts. And if you sum the 3 parts, we get that the original voltage whether it's VA or VB or VC. But so on the left hand side, we have the voltages A, B, and C. So VA, VB, VC, they are the phase voltages. On the right hand side, we have decomposed it into the sequence components. The zero sequence component, the positive sequence component, and the negative sequence component. Yeah, the sequence voltages on the right, phase voltages on the left of this equation. Yeah, so these voltages here are phase voltages, and these voltages here are sequence voltages, right? And then we know that if we actually consider a particular sequence, VA0, VB0, VC0, right? They are identical in magnitude and the same direction. If we consider the positive sequence components, VA plus, VB plus, and VC plus, they have the same magnitude, they are symmetrical, they differ only by the phase angle, right? VB plus 120 degrees behind VA plus, VC plus 120 degrees behind VB plus, because of the positive sequence. And the negative sequence, again, identical magnitudes, differ only by the phase angle. VB minus in this case, instead of being lagging VA minus by 120, it's actually VB minus is in front of VA minus by 120 degrees. And so is VC minus is in front of VB minus by 120 degrees, right? So we have some phase voltages, VA, VB, VC, which are not symmetrical. We decompose them into sequence voltages, right? And we can sum the sequence voltages to get the phase voltage on the left-hand side. And the sequence voltages have some symmetry. Yeah, that's what we have. So okay. So what we can do is we can just define, because we are talking about phase difference of 120 or 240. We can define alpha to be magnitude 1, phase angle 120, alpha squared, obviously alpha times alpha, so you magnitudes you multiply together to get 1. Angles you add together, so it becomes 240. So if alpha is 1 angle 120, alpha squared is 1 angle 240, and alpha cube will be, well, if you multiply 1 3 times, it's still 1. If you 120, if you add 3 times, you end up with 360. So alpha cube in fact is 1. And another thing that we notice is alpha plus alpha squared plus 1 is in fact 0, right? Complex numbers, if you add them up, it'll add up to 0. It's pretty obvious here, because if I add these real parts, it becomes 0. If I add the imaginary parts, it becomes 0. So we have this equation holds. What is something else we can say? For positive sequence voltages, right? For positive sequence voltages, so VA leads VB by 120 degrees. So VA plus leads VB plus by 120 degrees. So alpha times VB plus will be VA plus. And VB plus will lead VC plus by 120 degrees, so we can say that. So VB plus must equal alpha times VC plus, right? And in fact, we can also write VA plus leads VC by 240, right? So I can also say it's alpha squared VC plus, right? Because VC plus is behind, 240 degrees behind VA. Yeah? So these kind of relationships we can write. Yeah? So if we, yeah. So let me. All right, so by definition, we have this, all these zero sequence voltages are the same, right? So we can say, we can write this expression. What did we write before? We said VA plus must equal alpha times VB plus, right? We said that because VA is 120 degrees in front of VB plus. So if I multiply both sides by alpha squared, this will be alpha squared and this will be alpha cube, and alpha cube is 1, so we end up with this expression. So we can say VB plus is alpha squared VA plus, right? And VC plus, what did we say before? VA plus must equal alpha squared VC plus, because VA is 240 degrees in front of VC plus. So again, if I multiply by alpha by both sides, this will be alpha cube, so which is 1. So we have VC plus equals alpha times VA plus, right? So likewise, we can write these relationships as well. Okay, for negative sequence, we know that VB minus is in front of VA minus by 120 degrees. We know that. So that's that relationship here. VC minus is 240 degrees in front of VA minus. So I think this should be VA minus. Must equal alpha squared VA minus. Yeah? So there's a typo here. Yeah? So what we can do now, we can actually utilize those relationships to express what VA, VB, and VC is. Because VB plus is related to VA plus, VB minus is related to VA minus, VA minus is related to VC minus, and so on. You can see that. Yeah? So here we have VA minus related to VC minus, VA minus related to VB minus, we have VA plus related to VB plus, we have VA plus related to VC plus, and so on, right? We have these relationships. So what do we know? We know that VA must equal VA 0, zero sequence voltage, positive sequence voltage, and negative sequence voltage. So that's exactly what we see here. That's exactly what you see here. VA must equal the zero sequence voltage, positive sequence voltage, and the negative sequence voltage, right? In other words, all this multiplied by that will give you VA. Now VB, we know that VB is equal to VB0 plus VB plus VB minus, but of course they are also related to VA plus and VA minus. So we can write this relationship. VB must equal those terms, 1 alpha square and alpha, multiplied by the zero sequence voltage, positive sequence voltage, and negative sequence voltage of A. Likewise, we can write VC in terms of the zero sequence positive and negative sequence voltages for A. Right? So what do we have here? So what do we have here? What do we have here? Okay. What do we have here? If you focus on this part, that is the phase voltages, VA, VB, VC. If you focus on this part here, what is that? That's the sequence voltages, right? The sequence voltages. sequence voltages for A, zero sequence voltage of A, positive sequence voltage of A, negative sequence voltage of A, and what you see here is some metrics, some numbers. You know what alpha is, you know what alpha squared is. So we now have this relationship. The phase voltages, Vp is the phase voltages, which is Va, Vb and Vc, is related to sequence voltages, which is Va0, Va plus, Va minus. They are related through a transformation matrix A, which is that, through a transformation matrix A. So we can say the phase voltages Vp must equal the transformation matrix A multiplied by the sequence voltages. So what this tells me is that if I know the sequence voltages, I can calculate the phase voltages. Or other way around, if I have the phase voltages, I can also calculate the sequence voltage Vs by A inverse Vp. Right? Yeah. So from the phase voltages, we can calculate sequence voltages. From sequence voltages, we can calculate phase voltages. And the same relationship holds for currents. In other words, if I have the phase currents, Ia, Ib, Ic, they are related to the sequence currents through this matrix A. So Ip must equal A times Is. If I know the sequence currents, I can know the phase currents. If I know the phase currents, I can also know the sequence currents. Can go both ways, right? So if we define the sequence voltages, so Vs is the sequence voltages, is the zero sequence voltage, positive sequence voltage, and negative sequence voltage, right? The phase voltages Vp is a vector, Vs is a vector, Vp is Va, Vb, and Vc, voltages in phase A circuit, phase B circuit, and phase C circuit. Then we can write this relationship. Vp, phase voltages, is the matrix A multiplied by Vs. So as I said before, Vs must equal A inverse Vp, and if A is given by this matrix, then of course this 3 by 3 matrix we can compute its inverse, and you can verify it's going to be that. One way to verify that is to multiply A and A inverse, and you will obtain the identity matrix. That verification you can easily do, right? These relationships are valid for not only valid for voltages, they are also valid for currents. Phase currents is related to the sequence currents, right? Okay, so we have now an example, right? So current in phase A is 10 angle 0, current in phase B is 10 angle minus 120, current in phase C is 10 angle positive 120. So can you tell me if these currents are balanced or not? They are balanced, right? A has an angle 0, B is lagging A by 120, and C is lagging B by 120 as well. So they are actually symmetrical. But let's compute the sequence components and see what's the situation for this. So the sequence components are A inverse times the phase current, I, right? So here is A inverse, here is the phase current. So if you compute, this is the result you're going to get. So what is important here? Zero sequence component is 0. Negative sequence component is 0. We only have a value for positive sequence components, which is 10 angle 0, which is that. Right? So IA, if I want to calculate IA, right, IA, IB, IC would be matrix A, which is 1, 1, 1, multiplied by 0 sequence component, positive sequence component, and negative sequence component. And then you can see the 0 sequence component is 0, negative sequence component is 0, only a positive sequence component there, you will get this answer, 10 angle 0. Right? So the current we are looking at is symmetrical, therefore it had 0 sequence component and 0 negative sequence component, only we have a positive sequence component as expected. Okay? So let's look at another example. Let's look at another example. Let's look at this current. So here we have IA 10 angle 0, IB is 10 angle 120, which means now it's 120 degrees in front of A, and C is another 120 degrees in front of B, or 120 degrees behind A, same thing. So you can see this is a negative sequence current, really. Yeah, it's symmetrical, but the sequence is reversed. So if you now calculate the sequence currents, 0 sequence will be 0, positive sequence will be 0, negative sequence will have a value of 10 angle 0. You can do the calculations and see, right? If you do the calculations, that's what you're going to find out. So this example, we still, like, you know, for the phase currents, we can choose unbalanced currents, but we chose balanced current. So the balanced currents here, the phase sequence is ABC, right? Here phase currents are balanced, the phase sequence is not ABC, it's reversed. So that's why we have a negative sequence current and the other sequence currents are all 0. In this situation, we have the positive sequence current, we have a value, and all the other sequence currents are 0. Right? So here is another example, right? So this example here, 5 angle 90 for VA, 8 angle 150 for VB, VC is 8 angle minus 30. So the phase voltages are not balanced. Because they are not balanced, when I compute the sequence components, I expect to see a 0 sequence component, positive sequence component, and a negative sequence component, because it's not balanced. Phase voltages are not balanced. So my objective here is now to calculate the sequence voltages. So sequence voltages can be calculated using that, right, relationship. Sequence voltage is A inverse times the phase voltage. So here is the A inverse. Here are the phase voltages, and when you compute, we get these 3 values. So the first value here is the 0 sequence component, here is the positive sequence component, and here is the negative sequence component. Right? So as expected, we are now having all the components present here compared to some of the components, sequence components are 0 here because the phase voltages were balanced. All right, so here 0 positive and negative sequence of impedance loads. Consider a balanced Y impedance load. So you have, okay, so you have ZY, that's balanced, ZY balanced, ZY balanced. So that's a balanced load, right? Consider a balanced Y impedance load. The impedance of each phase is designated ZY, and the neutral impedance is Zn. So neutral impedance is Zn. So we take the neutral and we connect it to ground. So there's a path like that, right? And that is Zn. It's connected between the load and the neutral ground. Okay, you take the neutral point and you connect it to ground. We can now have the following equations. Okay, what are the equations that we can have? We have current IA, right, flows like that, and then it can flow like that, right? Now the current that flows IN, right, the current that flows through path B also flows to the neutral, Zn, impedance Zn to the ground. Current that flows through line C flows through ZY and flows to the ground through Zn, right? So we can write this equation. VAG is a voltage at point A relative to ground. This is point G, right? Yeah, is the drop across ZY plus the drop across Zn, right? So the current that flows in here is IA, current that flows in here is IA plus IB plus IC, right? Yeah, so we can write this: VAG must equal ZYIA, Zn IN is IA plus IB plus IC. So we can now write, we can just simplify it. So you have ZY plus Zn, so this term and this term, multiplied by IA, Zn multiplied by IB, Zn multiplied by IZ. And similarly, we can write expression for VBG and VCG. And if you write these expressions, then you know that this diagonal terms is going to be ZY plus Zn, and all the other terms are Zn, right? Simple verification that you can make. So we have this expression on the right hand, on the left hand side we have the phase voltage, then we have some impedance, we'll call it phase impedance matrix. On the right hand side we have the current vector, the phase current vector IP. So we can say Vp is equal to Zp times Ip. Yeah, phase voltage vector, we have on the right we have the current voltage vector, phase current vector, and then Zp is impedance matrix, phase impedance matrix. All right, so what can we say now? We know that phase voltage is related to sequence voltages through this relationship, A times Vs. We also know that Vp must equal Zp Ip, right? Impedance matrix Zp multiplied by the phase currents. Okay, now we also know that Ip can be written as A times Is, A times the sequence current. The phase currents must equal A times the sequence currents. So Vp is A times Vs, right? So now I can say Vs is A inverse Zp A times Is, right? And I can define that to be Z impedance matrix, sequence impedance matrix. So Vs is therefore Zs times Is. And what is Zs? Zs is A inverse Zp times A. Right? So we know what Zp is. Zp is this guy here, is Zp. We know what A inverse is, we know what A is, so we can actually do that multiplication and then arrive at Zs as this diagonal matrix. Zx, Zs is the diagonal matrix if you do the multiplication. So we now have this relationship. The the sequence voltages must equal this diagonal matrix multiplied by the sequence currents, right? And you can also see this matrix is diagonal, off diagonal terms are all 0. What that means is that we have a decoupled system. Zero sequence is decoupled with the positive sequence, is decoupled with the negative sequence. That's what we have. We have a decoupled system. So we can then say zero sequence voltage is Zy plus 3Zn multiplied by the zero sequence current. Positive sequence voltage is Zy times the positive sequence current. Negative sequence voltage is the Zy times the negative sequence current. Just expanding the matrix of diagonal terms are all 0. So we can now, based on these three equations, they are decoupled. We can draw three separate circuits. Zero sequence impedance is that. Positive sequence impedance is Zy. Negative sequence impedance is Zy. So we can draw these equations, these three circuits. Zero sequence impedance is Zy and 3 times Zn. Positive sequence network is just Zy. Negative sequence impedance circuit is just Zy. Right? So we can take, so what are we having? We just have something like this. We have a star network, right? The star network had Zy. Zy. This is what we have, right? Zy. This is a star network. Something like that. And then what do we have? We have Zn connecting into ground, Zn connecting to ground, isn't it? That's what we have. So if we now want to take this network and draw the zero sequence, the positive sequence and negative sequence networks corresponding to what we see here, right? The zero sequence will simply have this Zy, it will have the Zy and 3 times Zn, 3 times Zn, 3 times that, and you will have that. You will have Zy and 3 times Zn. That's a zero sequence network. Positive sequence network will have just Zy. Here it is, just the Zy. The negative sequence network will simply have Zy, doesn't have Zn. Right? So we have this network, we have corresponding zero sequence network, a positive sequence network, and a negative sequence network. So I can look at this configuration and say, okay, 3 times of that must appear in the zero sequence, and this term, this has to appear there for the zero sequence, which is this term and this term, impedances. For positive sequence, we're only going to have Zy. For the negative sequence, we're only going to have Zy. That's what we come up with. We came up with that through the equations, through the relevant equations, because we ended up with this set of equations for sequence relationships of voltages and currents, and we find that the three networks are decoupled because this matrix is diagonal. Right? That's what we have. So that's a star connection that we looked at, a star connection with the neutral point connected to ground. That's what we looked at. And now we're going to look at a delta network, delta impedance. So we have a delta impedance here. Okay. So with the delta impedance, we can translate that into a star network by taking the impedance and dividing by 3, which is what you see on the right. So in the middle you have a neutral. The delta network there is no neutral and it's not connected to ground. Right? Delta network doesn't have a neutral and it doesn't connect to ground. So in the star network, although we have the neutral, which is the center, which is where all the lines connect, that point neutral will not be connected to ground, because the delta network, nothing is connected to ground, right? So in other words, we can think that neutral network, between the neutral network and the ground, there is infinite impedance, because it's not connected, right? N is not connected to ground, so it has infinite impedance. So then how can we draw the sequence networks based on what we know? Well, if you have a star network like this, zero sequence network will have this impedance value, Z513 plus 3 times infinity, right? 3 times infinity. So in other words, well, this is that Z513 is that, this is the Z513, and this is the infinite impedance, because there's nothing connecting the neutral to the ground, right? Positive sequence network will simply have Z513. Negative sequence impedance will simply have Z513. That's it. Those are the 3 sequence network corresponding to a delta load. Right? Yeah. So now sequence 0 positive and negative sequences of 0 impedances, series impedances is what we are going to look at. So you have line A and A dash, points A and A dash, and you have a series impedance ZAA. You have point C and C dash, and you have an impedance ZCC between them. You have the points B and B dash, and you have a series impedance ZBB between the 2 points. So the figure shows series impedances connected between 2 3-phase buses denoted ABC and A dash B dash C dash. Self impedances of each of those are denoted ZAA, ZBB, and ZCC. So they are the self impedances. ZAB and ZAC are called mutual impedances between the lines. So we can write the voltage drop between point A and A dash, VAN minus VA dash. So A is on the left hand side, A dash is on the right hand side. Same with B and C on the left hand side, B dash and C dash on the right hand side. So VAN minus VAN dash, right? So VAN is the voltage between A and the neutral. A dash N is this voltage here, A dash and N, right? So is equal to VAA dash, so voltage between A and A dash, right? Voltage between A and A dash is given by these impedances multiplied by these currents. So ZAA, which is the self impedance, multiplied by current IA, and mutual impedances ZAB multiplied by IB, ZAC multiplied by IC, and so on. So the mutual impedance values, self impedance values are on the diagonal. Okay. So we can write in matrix form VP. So this is VP minus VP dash. This vector here is VP dash, right? Must equal ZP. ZP is this guy here, multiplied by IP. IP is phase current. IB, IA, IB, IC. So we have that compact form. We've written the same equation in compact form using matrix notation. And those are the phase values, and we can also consider the sequence values. So Vs minus Vs dash to be Zs times sequence matrix multiplied by the sequence currents. And then we know that the sequence matrix is A inverse ZPA. We derived that. And if we assume the series impedances are symmetrical, in other words, ZAA self-impedance values, AA, BB, and CC, they are the same, and mutual impedance values are the same. If we assume symmetry in the impedances, and we compute ZS sequence impedance matrix, if you do this calculation, which I encourage you to do, right, you will get this diagonal matrix. And in the 1, 1, you will get the 0 sequence impedance, positive sequence impedance, and the negative sequence impedance. What is Z0 is ZAA plus 2 ZAB. What is the positive sequence impedances is given by the self-impedance minus the mutual impedance between A and B. And you have these relationships because we have Vs minus Vs dash is Zs times Is. Vs is a vector, right, which has V0, V plus, and V minus. Vs dash again has the 0 positive and negative sequence components, so we have these values, is in fact that part. Must equal Zs is a diagonal matrix, which is this one, multiplied by the current, sequence currents, so we end up with these 3 decoupled equations, simply because this term here is a diagonal matrix. So we end up with that. So based on that, now we can draw 3 networks. Zero sequence network. Zero sequence network will just have this impedance ZAA plus 2 times ZAB. The positive and negative sequence impedances would be that. So we have a positive sequence impedance and a negative sequence impedance, which is the same. So we have this 3 sequence network representing this network that we talked about. So what have we done so far? We've looked at star connected load and the neutral connecting to ground. We looked at the sequence circuits for that. We've looked at a delta connected load, and then we looked at the sequence circuits for that, and we looked at the series impedances and the sequence network for that. 3 sequence networks for that is what we have, right? So what we now want to do, so basically we are taking different networks and drawing corresponding 3 sequence networks for each of those. That's what we are doing. So here we have a generator, right? So generator has an internal voltage and has some impedance so that's the terminal of the generator, that's the neutral point. So we have 3 such generators, and the neutral point is connected to ground, right? So we want to now know what are the sequence network that represent all that. What are the sequence? What is the zero sequence network? What is the positive sequence network? And what is the negative sequence network? So the zero sequence network, we have, remember Zn, the zero sequence network needs to have 3 times Zn. That's 3 times Zn, right? Because there is a path from ground to the neutral. So if there is a path from ground to the neutral, zero sequence current can flow. If there is no path from ground to the neutral, zero sequence current can't flow, and there will be an open circuit like we saw in the delta network, right? Because if there is no path, that means that Zn is infinite. So that's an open circuit. So then it needs to have, the zero sequence need to have this impedance here. So impedance of the generator, right? 3 times the Zn, impedance of the generator. Positive sequence circuit is simply this generator voltage and this positive sequence impedance. This is a generator, positive sequence impedance. So the impedance that connects to the ground doesn't appear. Zn doesn't appear. This term doesn't appear. The negative sequence voltage is identical to the positive sequence, right? Except there is no voltage source. So there is no source here. And this impedance is, instead of the positive sequence impedance values, it's the negative sequence impedance values, right? So what we have here, we have this generator configuration. It's a balance, this system. And we have 3 sequence circuits. We represent that we have a zero sequence, a positive sequence, and a negative sequence. All right, so if we are talking about a motor, so instead of this being generator, this is a motor. The only difference is the current just going to flow into the motor instead of flowing out of the generator. Currents flow into the motor. With the generator, currents flow out, right? So it's the same circuit as the generator. It's the same circuit as this. This current will be reversed. It's the same thing. So the currents are reversed. So here the currents are reversed. Same circuit. Currents are flowing in. If it's a motor that we are talking about, right? Currents are flowing in instead of flowing out of the terminal. Currents are flowing into the terminal if it's a motor. All right. So we're going to look at an example. So I think we'll take a very short break, maybe a 5-minute break, and we'll come back and then we'll continue with the examples. So see you soon. All right, let's continue. Here is an example. A balanced positive Y-connected voltage source with EAB equal to 480 angle 0. So here is point A. Here is point A, here is point B. So these three voltage sources are balanced. So VAB is 480 angle 0, so that's line to line voltage, is applied to a balanced delta load which has impedance 30 angle 40. So that delta load has been connected to Y, and when we connect a delta to Y, we divide the impedance by 3. So here we have divided by 3. Since it's a delta, so the neutral point is not connected to the ground. So that's an important point to note. Neutral point is not connected to the ground. The line impedance between the load and the source is 1 angle 85. So this is 1 angle 85, right? Draw the sequence networks for the circuit and calculate the sequence components of the line current. So we want to draw the sequence networks, the zero sequence, the positive sequence and negative sequence, and then we need to calculate the sequence components of the line currents. Assume the generator neutral is grounded through an impedance. So this is grounded through some kind of an impedance Zn, which is given by J10. And the generator sequence impedances, zero sequence is 1 ohm, positive sequence is 15, J15, zero sequence is J1, and negative sequence is J3. Okay. So here we draw the positive sequence. Remember, the generator is grounded, so it's 3 times the value of the impedance that grounds the generator. This is the zero sequence impedance of the generator, zero sequence impedance of the line, zero sequence impedance of the delta load, and then the neutral is not connected to the ground. So that's the neutral and that's the ground is not connected. Neutral and ground, there is infinite impedance. So the zero sequence current will be 0, right? So what is then the positive sequence circuit? Well, we have the internal voltage of the generator. We have the positive sequence impedance of the generator. We have the positive sequence impedance of the line. We have the impedance of the load, right? And that's it. Because we don't consider a grounding of a neutral when you're talking about the loads, positive sequence. We don't, right? So that's the positive sequence circuit. Negative sequence circuit is exactly the same without the voltage source. So we have the negative sequence impedance of the generator, negative sequence impedance of the line, negative sequence impedance of the load, and that's it. So here the negative sequence current is also 0 because there's nothing driving it. So the only thing that we have is the positive sequence current, right? And that is expected because this is a balanced circuit. So we are not expecting any zero sequence or negative sequence currents because it's a balanced circuit. And that's exactly what we see here. So then what is the positive sequence current? Well, we know this voltage, we know the impedance values. If you divide the voltage by impedance values, voltage by the impedance values, we get the current, which is that, which is in fact IA. Why is it IA? Because remember, IA, IB, IC, right, is equal to A times the 0 sequence, the positive sequence, and the negative sequence. So that is 0, that is 0, right? That is 0. We have something here, and matrix A is 1, 1, 1, remember? And then these are some other things, doesn't matter. So this is 1, 1, 1 multiplied by that gives you IA, right? And that is expected. So IA is the positive sequence current. So here we have example 2, a Y-connected voltage source with the following unbalanced voltages. So we have a Y-connected voltage source, but they are unbalanced. A to ground is that, B to ground, so this is, let's say, A, say this is B, they say this is C. A to ground we have one value, B to ground we have another value, C to ground we have another values. The source neutral is solidly grounded, so this is solidly grounded, so that's the ground, right? A to ground, B to, so there is solidly grounded, so there is nothing there, right? No impedance value is 0. Is solidly grounded. Using the method of symmetrical components, calculate IA, IB, and IC. Right? We need to calculate IA, IB, and IC. Okay. So we have this relationship. Sequence voltages are A inverse times the phase voltages. The phase voltages are these guys here. Sorry, phase voltages are these guys here. We knew that. We know that. They are given. Right? We know them. They are given, which is this guy, which is this, which is that. Right? This vector here is this vector here. This we know. So we can calculate the sequence values. These are the sequence values. Matrix A multiply, where A inverse multiplied by the phase values will give us the sequence values. Right? So here is the zero sequence. So zero sequence circuit is given here. We have a zero sequence voltage now. Zero sequence voltage is this guy here. We compute that. We have a zero sequence voltage. We have the line. We have the line impedance, right? We don't have 3 times Zn here because Zn is 0. So there is no 3 times Zn. That's 0. This term is 0. We don't have that. So this is the line impedance. This is the load impedance. Right? This is the load impedance. Right? Because it's connected to a, remember, a delta. So the delta, we represent it as a star by dividing by 3. This is linked to the first question, right? This second example is linked to the first example. It's talking about the same load. But the load is not connected to ground. So this is the neutral, this is the ground. Load is not connected to the ground. So there is an open circuit there. Load is not connected to the ground. Yeah. Positive sequence, here is the positive sequence, voltage, line impedance, load impedance. The circuit for negative sequence is the same, but we have different voltage magnitude, line impedance, and load impedance. So these are the 3 separate circuits. So we can now calculate the positive sequence current, negative sequence current, zero sequence current is 0 because of this open circuit here. So these are the calculations for the positive sequence, and the negative sequence is simply divide the voltage by the impedance in the circuit. Circuit is very straightforward, very trivial. And once you have the sequence values, then you can compute IABC by multiplying by transformation matrix A, pre-multiplying by matrix A. So those are the currents. So here we have an unbalanced generator connect to a balanced load, and this is what we have. Right? So we use symmetrical components here to study an unbalanced circuit. The generators were unbalanced. Yeah. So you can calculate the line currents for this example without using symmetrical components to verify the result and to compare the two solutions. You can also do it without using symmetrical components. Kirchhoff's voltage law, Kirchhoff's current law, because you have a network, right? You can just apply Kirchhoff's voltage law and current law, and you can solve this using, KVL, KVL, solve it and see if you get the same answers. So that will be a good exercise to do. Okay? With symmetrical conversions, the conversion from phase to sequence component decouples the circuit as well as the resulting KVL equation, because it decouples. Because you, instead of analyzing one circuit, you analyze three different circuits. Right? But it will be interesting to see if you can actually get the same answer by just without decoupling the circuit into three sequence circuits by using KVL. Just analyze the circuit to see if you get the same answer. So what we have done, we've looked at sequence circuits for generators, for motors, for star connected loads, delta connected loads, and series impedances. We've considered the sequence circuits, and now we are going to look at, okay, how do we draw the three separate sequence circuits for transformer, right? Because there could be transformers in a network. All right, so here we are looking at a Y-Y connected ideal transformer, right? Y-Y connection. It's an ideal transformer. So the Y-Y connected ideal transformers are the easiest to understand, which is shown below. So the neutral point here on the primary is connected to ground through Zn. A neutral point on the secondary is also connected to ground via Zn. The sequence network for Y-Y ideal transformer are shown below. Right? Z uppercase n and Z lowercase n. So here, because your neutral is connected to ground, right, your zero sequence current can flow. For zero sequence current to flow, there has to be a path between ground and the neutral. Without a path and the ground and the neutral, without a path, the zero sequence current can't flow. So zero sequence current can flow on the primary side. It can also flow in the secondary side because both neutral points are grounded, right? And when we draw the sequence circuits, remember, we take that and you multiply by 3. So here are the primary terminals on the left. You have the secondary terminals on the right. So the zero sequence currents can flow in the primary, and it will flow through 3 times Zn, which is this. And the current, zero sequence current in the secondary will flow through 3 times Zn in the secondary. So the zero sequence circuit for a Y-Y connection with the neutral connect to the ground is shown here, right? So when per unit sequence currents IA0, IB0, IC0, which is I0, right, are applied to the high voltage windings of an ideal Y-Y transformer, the neutral current IN is 3 times I0 flows through the neutral impedance Zn with voltage drop 3 times Zn I0. Also per unit zero sequence current I0 flows in each low voltage windings, and therefore 3 times I0 flows through the neutral impedance Zn with a voltage drop of 3 Zn I0. So that's what we see here. So positive sequence and the negative sequence, this Zns doesn't matter, which connects to ground, and there is no series impedance. It's ideal transformer. You know the ideal transformer equivalent circuit does not have any shunt impedances, does not have any series impedances. So its positive sequence is just the primary and secondary just connecting like that. Negative sequence is the same, primary and secondary connecting in this way. There are no impedances. When balanced positive sequence currents or balanced negative sequence currents are applied to the transformer, the neutral currents are zero and there are no voltage drop across the neutral impedances. B and C demonstrates this feature, circuit B and circuit C. Right. So here we are looking at a non-ideal transformer. So you have the Y on the primary, Y on the primary, Y on the secondary. The neutral points of both primary and secondary are grounded, right? So what you see here, what is the zero sequence? So here 3 times Zn appears there, 3 times Zn appears there for the secondary, and everything in C that what you see here is just the equivalent circuit of the transformer. Yeah, equivalent circuit of the transformer. So positive sequence, well, the Zns doesn't appear. This is the equivalent circuit of the transformer. Negative sequence, well, that's the equivalent circuit of the transformer. Right? Yeah. So here we are looking at a Y delta connection of a transformer. The Y, the neutral is connected to ground. Yeah. So delta, there is no neutral. So on the primary, zero sequence current can flow because there is a connection between the neutral and the ground. So here is the 3 times Zn. Here is the transformer equivalent circuit, right? So on the delta, the zero sequence currents can flow inside the delta, but it can't flow out of the terminal because there is no path from the neutral to the ground. Because there is no path from neutral to the ground, no currents can enter or leave the secondary side of the transformer. Right? So that's why here the terminals on the secondary is not connected to the primary. It's not connected to the equivalent circuit of the transformer because the zero sequence current can't flow out or flow in. Yeah, so that's what that represents. So this terminal here, the equivalent circuit, this is grounded. So any currents has to be inside that. Only the zero sequence current can flow into the primary terminal. Yeah. So the positive sequence, well, that's the transformer equivalent circuit. Negative sequence the same, transformer equivalent circuit. Because you're going from Y to delta, there is a phase shift because line to neutral voltage and line to line voltages are out by 30 degrees. So here is the 30-degree shift. That's due to Y to delta transformation. Right? So here is a delta-delta connection. Again, this is the transformer equivalent circuit, right? Transformer equivalent circuit. Zero sequence currents, there is no connection from neutral to ground, so zero sequence currents cannot flow into the transformer, out of the transformer. So that's why the primary terminal here and secondary terminal here are not connected to the equivalent circuit of the transformer. Right? The positive sequence circuit, well, that's the transformer equivalent circuit, negative sequence transformer equivalent circuit, and the positive sequence impedance values and the negative sequence impedance values will be applicable in this situation. We'll go into those elements. We'll represent the impedances of those elements. All right. So now we have looked at zero positive and negative sequence circuits for transformers as well. All right, so here we are looking at an example. Let's look at an example. A 75 kilovolt amp, 480 volt delta, 208 volt Y transformer. So delta to Y, here is a delta, this is the Y. With solidly grounded neutral is connected between the source and the line, right? Is connected between the source and the line. So source is on the left, and that's the line is on the right. Right? The transformer leakage reactance is 0.1 per unit. Winding resistance and excitation currents are neglected. So there is no shunt branch because there is no excitation current, and there is no winding resistance. So the series impedance is just the reactance, the leakage reactance. Using the transformer ratings as base quantities, draw the per unit sequence networks and calculate the phase A source current IA. Right? So we have VAG, VBG, VCG given by these values. They are the source voltages, they are not balanced. Right? Primary side of the transformer is connected to the source, and the secondary side transformer is connected to the line. Okay, and so we need to calculate the per unit values. So the base quantities, single phase power is going to be 75 volt amps, apparent power is 75 kilovolt amps divided by 3, so 25 kilovolt amps per phase. On the primary, line to line voltage is 480, and the secondary 208. So on the primary side, line to neutral is 480 divided by root 3. On the secondary, 208 divided by root 3. So the base impedance on the secondary side would be the apparent power, the voltage squared on the secondary side, which is 120.1 squared, divided by the apparent power, which is for the single phase. So that will give us the base impedance. The sequence components of the actual source voltages are given in the last example, which is shown below, right? So these are the sequence voltages. We calculated that in the previous example. Right? When we have the phase voltages, these ones, we calculated the sequence voltages, which is the previous example, we calculated it. Here, these values, right? These values we calculated. So those are the values we calculated in the previous example. These are the sequence values. So now we want to find the per unit values. So per unit values on the secondary side you divide by the base values of the, on the primary side, you divide by the base values on the primary side, because the generator is connected to the primary side of the transformer, not the secondary side. Primary side, the voltage value is that, right, 277.1, because the generator is connected onto this side. This is the generator, that's the primary side, right, 480 divided by root 3, which is this value here. So we can then calculate by dividing by the base values on the primary side, we can actually calculate the per unit values of this sequence voltages for the generator. Per unit load impedances, we calculate the base value on the secondary side of the transformer, because the load is connected to the secondary side of the transformer. So we know the values of the load and the line, they are connected to the secondary side of the transformer. So we divide by the base values on the secondary side of the transformer to get the per unit, these per unit values, right? So then we can draw now the sequence circuit. So we have a generator, okay? Generator is connected to a delta transformer, right? Delta transformer. Now delta transformer does not have a neutral, right? So the zero sequence can't flow into the delta transformer. So here is the transformer. This is the transformer just by a series, represented by series reactance, right? The zero sequence current can't flow into the delta. So there is an open circuit here. So that connects to the ground. This is the line and this is the load. Again, the load is delta, so there is no connection between neutral and ground. So here is the neutral point, here is the ground point. So there is an open circuit there as well. So the zero sequence current that is flowing out of the generator is zero, because it can't flow into the delta network. And here is a positive sequence circuit. Positive sequence circuit, the positive sequence value is this, we computed that. This is the series reactance. This is the line impedance. This is the load impedance, right? So we know this value, we know the impedance value, so we can calculate this current. Negative sequence circuit, again, we have an impedance, voltage source. We have the reactance of the generator, line impedance and the load impedance. Again, we have the voltage divided by these impedances, so we can actually calculate the current I minus. So I0 is 0, I plus we calculate it by dividing the voltage of the generator, positive sequence, divided by the positive sequence loads. Negative sequence current, again we calculated in the same way, and once you have the positive, zero, positive and negative sequence currents, by multiplying by, pre-multiplying by matrix A, you can calculate all these currents, I, A, B and C, which is what the question is asking. Right? And then once you have this per unit value, you want to convert it to the actual value, you can multiply by the base value, and you can obtain the actual value. So we have talked about positive sequence circuits, zero sequence circuits, negative sequence circuits. We've learned how to draw those circuits, right? What we now need to do is to use all that understanding to do fault calculations. We haven't talked about that yet. So finally I have gone through all the necessary knowledge and reached the false part, which is this one. In our study we look at three types of asymmetrical faults: single line to ground, line to line faults, and double line to ground faults. A three-phase power system is represented by its sequence networks in fault analysis, right? The zero, positive, and negative sequence networks of the components, generators, motors, transformers, transmission lines. You know how to draw the sequence networks for all those types as developed in section 6.1, and we're going to use all that knowledge now to do fault calculations. And in doing the fault calculations, we make the following assumptions. We assume the power system operates under balanced steady state conditions before the fault occurs. Thus, the zero, positive, and negative sequence networks are uncoupled before the fault occurs. Before the fault occurs, because they are balanced, that means they are uncoupled. During unsymmetrical faults, they are interconnected only at the fault location. So when the fault occurs, the system will be unbalanced, and the circuits will be coupled, and it will only be coupled at the point where the fault occurs. Pre-fault load current is neglected in our calculations. Because of this, the positive sequence internal voltages of all the machines are equal to the pre-fault voltage. So the pre-fault voltage will be, well, voltage of the positive sequence internal voltage of all the machines will be the pre-fault voltage, because we are going to assume that pre-fault load current is neglected. We assume zero. Therefore, the pre-fault voltage at each bus in the positive sequence network equals Vf. So at each bus where the fault occurs, the pre-fault voltage would be Vf. Pre-fault voltage at each bus in the positive sequence network is equal to Vf. That's an assumption. Transformer winding resistance and shunt admittances are neglected, right? So if at all, we will only include the series reactance for transformer equivalent model. Transmission line series reactance and shunt admittances are neglected. Synchronous machine armature resistance, saliency, and saturations are neglected. All rotating impedance loads are neglected. Induction motors are either neglected or represented in the same manner as synchronous machines. So some assumptions that we are going to make. So how are we going to do the calculations? This is an important part. There are three general steps in analyzing faults. Firstly, we draw the sequence networks for the pre-fault balanced uncoupled power systems, right? So we draw the pre-fault balanced uncoupled power system. We find the Thevenin impedance view from the faulted terminal. So at the faulted terminal, we find the Thevenin equivalent impedance, Thevenin circuit. Implement the fault calculations, implement the fault, and we calculate the desired quantities. So we have on the left, we have the zero sequence network, positive sequence network, and the negative sequence network, right? We then obtain where the fault occurs, we obtain a Thevenin equivalent at the fault terminal. Yeah? So for zero sequence, positive sequence network, and the negative sequence network, we have the Thevenin equivalent, which will look something like the right. So each sequence network has a Thevenin equivalent impedance. Also, positive sequence network has a Thevenin equivalent voltage source, which is equal to the pre-fault voltage Vf. So that voltage source magnitude in the positive sequence is the pre-fault voltage Vf. I think this will become clear when we look at an example. So we have a generator connected to a particular bus where the fault is going to occur. It's the internal voltage of that generator would be the pre-fault voltage Vf in this Thevenin circuit. It will become more clearer when we look at an example. So here is an example. So let's see how we can do the fault calculations. A single line diagram for power systems is shown below, right? So this is the single line diagram for a power system. You have a Y connected generator on the left with the neutral connected to the ground. You have Y connected motors on the right, and then the neutral is connected to ground. You have delta Y transformer on the left. Y is connected to the ground, or neutral, Y neutral is connected to the ground. On the transformer T2 is Y delta. Again, the neutral of the Y is connected to the ground. And the positive zero sequence, negative sequence impedances are given, right? X double dash is actually the positive sequence impedance, X double dash. X minus is the negative sequence impedance for the generator. X0 is the zero sequence impedance for the relevant impedance for the generator. Same can be said about the X double dash, X minus and X0 for the motor on the right. And then we have the impedance values for the transformer T1 and T2. You can see that. We have the voltage ratings for the delta and the Y. And we have the power ratings, which is apparent power of 100 megavolt amps for the transformer. And the generator rating is also 100 megavolt amps, and the motor on the right is 100 megavolt amps as well. So, what do we have? A single line diagram of the power system is shown below, which is what I've just showed you, where negative and zero sequence reactances are also given. We talked about that. The neutrals of the generator and delta Y transformers are solidly grounded. So there is no, it's a short circuit between the neutral and the ground. The motor neutral is grounded. Motor neutral is grounded through a reactance Xn of 0.05 per unit on the motor base. Draw the per unit zero positive and negative sequence networks on a 100 megavolt amp, 13.8 kilovolts base in the zone of the generator. So draw the per unit zero positive and negative sequence networks on 100 megawatt amp 13.8 kilovolt base in the zone of the generator, So here is the zero sequence. You have here the neutral and the ground are connected, so that's the neutral, that's the ground, right? So it's a short circuit, multiplied by 3 is still a short circuit. This is the zero sequence impedance for the generator. Generator then connects to a delta side of the transformer. So delta side of the transformer, there is no neutral connecting to a ground, so no zero sequence current can flow into it. So that's what this represents. No zero sequence current can flow into the primary side of the transformer. Here is the transformer equivalent circuit, the reactance, right? Here is the line reactance. This is the line. This is the transformer. And then that line connects to a transformer which is T2. Here is the reactance of the transformer. This is T2. This is T1. So again, primary side there can be zero sequence, but on the secondary no zero sequence current can flow out. So nothing can flow from there to that point, to bus 2. Zero sequence current can't flow into bus 2 because the delta is actually not grounded. So that's what that gap is representing, right? Here is the motor reactance, Here is the impedance that connects the motor neutral to the ground times 3. So that's the zero sequence network for the circuit that we see there. So you should be able to draw a circuit like this, zero sequence circuit, for an example like that. Yeah? You should be able to draw it. Right? Right. So positive sequence circuit is easy to draw. We have the generator, internal voltage, reactance of the generator, right? Reactance of the generator, right? Connected to the line, the transformer reactance, connected to the line, connected to the transformer reactance, connecting to the motor reactance and the motor internal voltage. It's straightforward. Negative sequence is exactly the same with these guys not present because it's a balanced operation until the fault. It's balanced. So those voltages are not there, and you put the relevant negative sequence reactances. So this reactance here is different to that reactance. Is the negative sequence reactance, right? So those are the 3 circuits. Yeah. So then in a fault calculation, the second step is you take the positive, the fault occurs on the motor side on bus 2. Okay. Fault occurs at bus 2. Now this is very important. Now you have drawn the 3 sequence circuits. The fault occurs at bus 2, which is this guy here, right? At bus 2. So we need to find the Thevenin equivalent circuit at bus 2. That's what this step is about. So what is the Thevenin equivalent circuit for bus 2 is just this part. That's it. So Thevenin equivalent circuit for bus 2 is just that. J.250, which is the sum of these 2 guys. Right? Circuit to the left is not relevant because it's just hanging, right, off the ground point. So the Thevenin equivalent circuit is just depends on what's on the left hand side, sorry, right hand side. So what is the Thevenin equivalent circuit or the positive sequence circuit? Well, across terminal 2, what we do, right? We find the equivalent impedance. When we find the equivalent impedance, we turn all the sources to 0, right? So motor source, you turn it to 0. Generator, you turn it to 0. So you have an impedance on the left hand side in series, right? These 3 guys you sum together, you have that. So this impedance here is in parallel with that impedance. Yeah? So that's the Thevenin impedance. So Thevenin impedance we can calculate, which is this guy here. Yeah? Thevenin impedance. Now, we said the pre-fault voltage here, like we assume that no current flows, so the pre-fault voltage is internal voltage of this motor then appears here, across there. That's VF, is 1.05 angle 0. Right? 1.05 angle 0. That's it. So all we do is we find the Thevenin impedance. We just take the internal voltage of this source, and then that is the pre-fault voltage. So it's not hard to do. And the Thevenin, then we look at the secondary, negative sequence circuit. Across 2, we have this impedance in parallel with that impedance, and then that's what it is. So here it is. Yeah, we do that calculation. So we now have, right, okay. So if the fault is a balanced 3-phase fault, if it's a balanced 3-phase fault, then we take the zero sequence circuit, Thevenin equivalent, we short circuit. We take the negative sequence circuit, we short circuit the terminal, right? we take the positive sequence circuit and we short circuit the terminal. That's a balanced three-phase circuit, balanced fault. We're looking at a balanced fault here. So the zero sequence current is 0, secondary negative sequence current is 0. A positive sequence current we can calculate because you have a voltage source and you have an impedance, divide the voltage source by impedance, we have a positive sequence current, right? So because this is now a balanced circuit, right? Balanced circuit we just implement by just putting a short circuit across the terminals, that's all we do. And we calculate the currents. So now we know the zero sequence current, positive sequence current, negative sequence current, we know them, which is this part here. Zero sequence is 0, negative sequence is 0, positive sequence we can calculate, we calculated it. So we can then calculate the currents that are flowing in A, B and C. I mean this is a balanced circuit, so IA, IB, IC are also balanced, they are out by just 120 degrees. Okay? We can calculate. Yeah. So far what I have done, I think I'm going to perhaps, because this is a bit unusual lecture because I'm delivering it via Zoom, right? And nobody in the class. I'm going to stop at this point and then I'm going to continue with this in the next lecture, but I just want to summarize what we've done, what I've done today. All we've done today is we've looked at, given an electrical network, how to draw the positive sequence circuit, the negative sequence circuit, and the zero sequence circuit corresponding to a given electrical network. Yeah? And once you know how to do that, so if there are transformers, generators, motors, loads, doesn't matter what it is, given an electrical network, we have figured out how to draw the zero sequence circuit, positive sequence circuit and negative sequence circuit. And when you have drawn those three separate circuits to do the fault calculations, what we're going to do, we said, where the fault occurs, at the bus terminal where the fault occurs, you find the Thevenin impedances for all three circuits. That is easy. If there are some source voltages and the positive sequence, you turn that to 0, you just find the Thevenin impedances, right? And then only the positive sequence circuit will have a voltage source, and that voltage source is the pre-fault voltage relevant to that terminal, which is the pre-fault voltage of the, in other words, the voltage of the internal voltage of the source that is connected to that terminal, which is going to have the fault. That is the pre-fault voltage, the internal voltage of the source, and that source is connected to the terminal where the fault is going to occur. So that's the pre-fault voltage that we are going to use in the positive sequence circuit. So here it is, positive, we have three circuits, the zero sequence circuit, the Thevenin equivalent at the bus where the fault is going to occur. We take the zero sequence circuit and we find the Thevenin equivalent, Thevenin impedance, and then that is the Thevenin circuit. This is the Thevenin impedance and that's the Thevenin circuit. Positive sequence voltage, again we find the Thevenin impedance, right? No problem at the terminal. Then we determine this value, this source here has to do with the source that is connected to that terminal and its internal voltage. So 1.05 angle 0 is the internal voltage of the source connected to that. Because here it is, the internal voltage is 1.05 connected to this terminal where the fault is going to occur. Okay, and the negative sequence circuit, you simply find the Thevenin equivalent impedance, right? at the terminal where the fault is going to occur. So we have these three circuits. These are the Thevenin values that we've computed. And this is the voltage source. This is the internal voltage of the source connected to the terminal where the fault is going to occur. Now, what we said in this example, if it's a balanced three-phase fault, in other words, all three lines are going to connect to ground, all we do is we connect a short circuit across all the three decoupled circuits, calculate the zero sequence current, negative sequence current. Obviously, they are going to be zero because there's no sources in any of those. We calculate the current in the positive sequence circuit, right? And once you have the sequence currents, then the phase currents you can calculate through that relationship, right? Through that relationship. Now, when we are going to do the calculations for other types, single line to line fault, or double line to ground fault, it's a question of how we going to connect the three sequence circuits is what's going to matter. Like in this situation, when there is a balanced three-phase fault, we knew we had to short circuit the terminals of the individual circuits. They're all still decoupled, and we can calculate the individual currents. Now, if it's a line to ground fault, we are not going to do what we just did. In other words, short circuiting the terminals and still have three decoupled circuits. We're going to connect the three circuits in some way. We're going to connect the three circuits. They're not going to be decoupled. They're going to be coupled. They're going to be in one circuit. We're going to connect them in some way and then do the calculations. So if it's a line to ground fault, we connect them in some way. If they are a double line fault, we connect them in a different way. If they are double line to ground fault, they will be connected in a different way. Just to tell you how to do that, I'm going to talk about this in the next lecture. If it's a line to ground fault, here is the zero sequence circuit, here is the positive sequence circuit, here is the negative sequence circuit. We connect them in series. Okay? When we connect them in series, all the three sequence currents are the same, but we can calculate them. So that's how you calculate, that's how you connect the three separate circuits for single line to ground fault calculations. Yeah? I will talk about that in a detail in the next lecture, but I'm just telling you, once you got the three circuits, it's how you connect it. How you connect it depends on the type of fault. So you connect in series if it's a single line to ground fault. You will connect the positive sequence circuit and the negative sequence circuit in parallel, and you ignore the zero sequence circuit if it's a line to line fault. And you ignore the zero sequence circuit. And you can also understand why that is. If it's a line to line fault, there is no connection to ground. So zero sequence current can't flow. So you ignore that. But I'm going to talk about that in more detail. Don't worry. I'm just telling you this is what you do. You take the positive sequence current circuit and negative sequence circuit and you connect them in parallel. And then you can do whatever, some calculations, find the positive sequence current and the negative sequence current, which is the same magnitude but opposite direction because the way it's marked. And then you can calculate everything, right? We'll talk about it later, but I'm just wanted to tell you that depending on the type of fault, we connect things in a different way. Here is a double line to ground fault. Here is a positive sequence circuit. Here is the negative sequence circuit. Here is the zero sequence circuit. And you connect all of them in parallel, right? And then you can do calculations as you wish. So the fault calculations, connection of the circuits for different fault calculations are going to be different. For balanced circuit for balanced fault, for three-phase to ground fault,